this is what I was trying to show about the collatz conjecture and the fast Fourier transform. First, collatz shortcut 3n plus 1 divide 2 seems to be missing information. So first up, we'll take all odd positive numbers from 1 to infinity. We'll put them in groups corresponding to base 10 or mod 10, as well as put 0 in the tens place for numbers less than 10. And there's that group. Now we will separate them into new groups corresponding to the even/odd value of their tens place number. 0, 1, 21, 41, 61. As you can see, we now have 10 groups that contain all odd numbers from 0, 1 to infinity. If we then apply 3n plus 1 to each number of these groups, each of which has an incremental difference of 20 increase from the previous low number, the group starting 0, 1 we will shift to 3n plus 1 even placement in the same order as the previous groups, which just means we'll go 0, 1, 21, 41, 61. And we'll get these groups. Appearing to have doubled the size of the groups by including 3 times odd plus 1 even numbers, we still contain all positive numbers 0, 1 to infinity, but we do not contain all positive even numbers from 0, 2 to infinity. We can run into other even numbers by randomly picking a positive number, and if even, divide by 2 to the power of n, or 3 times odd plus 1 divide by 2 to the power of n. The only way to obtain those missing even numbers is randomly choosing one or in a divisional sequence. But given even divided by 2 to the power of n, or 3 times odd plus 1 divided by 2 to the power of n, there will always be steps that hit an odd number, since all even numbers equal odd times 2 to the power of n. So far this is just standard collatz information with a slight visual distribution change. But with these new groups, you compare the odd inputs with their even output counterpart. And if you look at the even odd number of the tens place, you can still label them as 10 groups. Evens being B and odd being A. So we have odd 0, 1 to the power, or times 3 plus 1 equals 4, so that's labeled B1, B4. We have odd 11 times 3 plus 1 equals 34, so that's A1, A4. And then we get B3 that goes to A0, because 3 times 3 plus 1 is 10. 3 times 13 plus 1 is 40. A3, B0, as you can see. And with this, the 10 groups are established. And if you feed inputs of incremental increases of 20 from the starting point of the group, you will have outputs with incremental increases of 60. And of the 10 groups, the even outputs of 5 of them are divisible by 2 to the power of 2 plus n, and the divisibility of even outputs in the other 5 groups is just 2. We will focus on the latter, starting with, these are the 5 groups that are, when you take their even output and divide by 2, you automatically get an odd number. We will focus on group A9, A8. We will now label a set of groups inside of A9 to A8 from 1 to 8 and do it twice. Which means you run through the first 8, labeling it 1 through 8, and then when you go through a second time, you label it 1 through 8 again. So group 1 will have incremental increases of 1/6. A8, A9, A8, 1 will have incremental increases of 160 from 19 to 179. Group 2 will have, it'll all be incremental increases of 160. 39 to 199. As we can learn from this, group A9, A8 is that all 3 times odd plus 1 divide 2, or even numbers ending in A9 or in A8 divide 2 will become a number ending in A9 or B9. The odd number groups 1, 3, 5, and 7 go to B9, while groups 2, 4, 6, 8 goes to A9. Groups A9, A6, or A9, A8, 6 goes to 1 and 5. Groups 2 goes to 3 and 7. Group 4 goes to 2 and 6. Group 8 goes to 4 and 8. Group A9, A8 seems like a possible loop for some number to have infinite growth, so checking into it in more detail seems beneficial. We'll start backwards, starting at 3, 119, labeling it 8.2.1. And we'll continue this pattern for both 8.2 and 8.1. And if you notice, 8.2.1 is 479. That's 8.1.1. 8.2.3 with the output of 1439. Is 8.1.5. And so from this, we can figure out 8.1. Odd numbers go to groups 4.2. Number, and group 8.1. Even goes to group 1. Number. Following the same logic if we had split group 4 like we did group 8. And that also, group 4.1. Number goes to group 6. Number. and that group 4 2 dot number goes to group 2 dot number. But as far as for group A2 dot number, we can see group A2 dot odd goes to 8 1 dot number, and 8 2 dot even goes to 8 2 dot number. So we can write group 2 or group 8.2 dot number is 3 times 319 plus 320 times a number plus 1 divide 2 equals output A9 A8 group 8 dot number. It can go to 8.1 or 8.2 in the group 8 A9 A8. The n can be any number 0 to positive infinity. The odd numbers go to 8.2 even. And there's a small trend that we can pull that 8.2.2 goes to 8.2.3, and then because we know odds go to 8.2 or 8.1, that trend ends kind of there. But then 8.2.4 goes to 8.2.6, but then it goes to 8.2.9, and then there's another one after that. So if this trend continues, the amount of even outputs from 8.2 even going to 8.2 even will increase from going to 1, then 2, then 3, then 4, adding to the collatz orbit. And if it always ends in an even number, we know that it will always feed out to B9, to the group B9, B8. But if we can prove there is one instance of 8.2 even never going to 8.2 odd, then the collatz conjecture would be false. It is true that numbers up to the power of 68 have been proven to go to 1. So we can assume there is a large number 8.2 even that in turn goes to 8.2 odd. Now, the number of and I was just talking about this just adds to the collatz orbit, and it might not even increase specifically in that pattern. It can reset every little bit, which it kind of does. But if there does exist an instance where 8.2 even only goes to 8.2 even, then it'll never go to 1 because it'll prove infinite ascension. And with that formula, I added this. That way, after you divide by 2, if you subtract 319 and divide by 320, if it's 0.5, or if any number ends in 0.5, then it goes to the A9, A8 group, 8.1 point number. But when you get put in an odd output, it'll give you a whole number output, which is in the 8.2 group. But if it's even, it's going to, no matter what even number you put in, it's going to go to that other group. And if you increase starting from 1 and add increments of 4, all those odd numbers will always go to an even number. But if you start at 3 and add increments of 4, you'll get odd outputs. And what you want is a string starting with an odd out or an odd input that leads to the next odd input. And this is what I mean, because we know that 3 goes to 5, but if we go increment of 4, that's 7, so it doesn't go to 5, but 7 does go to 11, and 11 goes to 17, but there's no 17 in the input category. But 15 goes to 23, 23 goes to 35, 35 goes to 53, but 53 isn't there. $39 goes to 59. $31 goes to 47. And all you have to do to go to the next one is add 4 to 59, which will be 63, and then add 6 to the output, which would be 95. Add 4, add 6. Add 4. See, 47 goes to 71. 71 is an option. Add 6. There we go. And another thing is that when the input has a 9 at the end, the output will have a 9 at the end as well. And I think the longest string we had was 15, 23, 35, 53. We could just go back and check it. 23, 35, 53. And then I think 41 was, no. 40, yeah. 47 goes to 71. 71 goes to 107. And then 95. And that's what I meant by if you can find a string, an infinite string that starts at odd and it leads to the next input and all the inputs are odd, then the collatz conjecture is false. That's the simplest method. And I went into deeper detail on mapping out the fast Fourier transform using just the basic numbers as I showed you. I just don't know if anyone wants to see all that detail. Thank you for listening.